In this video, we'll look at the integral test and p-series. Suppose f is a continuous positive decreasing function on the interval from 1 to infinity, and let a sub n equal f of n. Then the series a sub n is convergent if and only if the improper integral is also convergent. Let's think about that in terms of a graph, just a quick sketch. First of all, we need a function which is essentially going to be a sub n, the sequence. We want it to be continuous, positive, and decreasing. So we're going to represent that sequence as a positive decreasing function. So think of it as almost like an upper bound to the sequence. If this integral converges, then we can say the series is convergent. Now we don't necessarily know the sum, but we can say that if the integral is convergent, then the series will be convergent as well. Similarly, if the integral is divergent, then we can say that the series is divergent. For example, we want to test whether or not this series is convergent or divergent. Let's treat f of x as x to the negative 1/3, or 1 over x cubed. A little bit later in this video, you'll learn that this is a p-series and there's a much faster way to attack this problem. But for now, we want to write this as an integral. In order to use the test, we need to make sure that this is continuous, and it is. The only issue we have with continuity is when x is 0, but that's going to be outside of the interval that we're looking at. So we do have continuous. We want to also make sure it's positive, and it is. It will never be negative. It is positive, again, on the interval. And it is decreasing. So we have decreasing as your x values or n values, whichever way you want to think of it, as those increase, then the fraction is decreasing. It's getting smaller. So we can use the test, which says we want to integrate from 1 to infinity. We'll use that improper integral, x to the negative 3 dx. So we need to take the limit as, let's use t approaches infinity, of x to the negative 2 divided by negative 2, evaluating that integral, and we're going from 1 to t. We now have the limit as t approaches infinity. Now plugging in those limits of integration, we get t to the negative 2 divided by negative 2 minus 1 to the negative 2 divided by negative 2. Let's come down here and just copy the limit for now. Inside those brackets, let's rewrite this as negative 1/2, and t to the 2 is in the denominator, minus, actually that'll be plus the double negatives, 1 divided by 2. And now we can evaluate the limit. As this t gets really big, the denominator goes big, fraction goes smaller, and this is just a constant, so we're getting 1/2. So this means that the improper integral converges. With that, we can now say the series converges. And we know it's going to converge due to the integral test. In our next example, let's again use the integral test. This time let's let f be the sequence that we have, 2 divided by 5n minus 1. We can see that this is positive, it's decreasing, and it's continuous on the interval that we're looking for, which will be 1 to infinity. So we have the integral from 1 to infinity of 2 divided by 5x minus 1 dx. So we'll take the limit as t goes to infinity, integral 1 to t of 2 divided by 5x minus 1 dx. That is the limit as t approaches infinity of, we have 2 divided by 5x minus 1. That's going to be 2 is just a constant in the numerator. And then we have the natural log of the argument, the denominator, 5x minus 1. And then we need to divide that by the derivative of 5x minus 1, which is 5. And we are evaluating from 1 to t. Let's now plug in those limits of integration. Limit as t approaches infinity of 2/5 ln of 5t minus 1 minus 2/5 natural log of, if we plug in 1 to this, we get 4. Now evaluating the limit, t is going to infinity. So inside this part, t is getting big. The natural log of a big number is a big number. And then this is just a constant. So we have infinity minus a constant. This is diverging. It's going to infinity. Since the improper integral diverges, improper integral diverges, that tells us the series from n equals 1 to infinity of 2 divided by 5n minus 1 also diverges due to the integral test. Up next we have the p-series. Note that the p-series is the sum from n equals 1 to infinity of 1 divided by n raised to the p. So we can think of this as 1 divided by, notice that the base is n, so the base is what's changing. We have 1 to the p plus 1 divided by 2 to the p plus 1 divided by 3 to the p, and so on. And the rule is, if p is greater than 1, strictly greater than 1, we have a convergent series. And it's going to diverge if p is less than or equal to 1. For example, if we have 1 divided by n raised to the square root of 2. First of all, recognize that this is a p-series. And since it's a p-series, we really just need to look at the p-value. The p-value is the square root of 2. P is square root of 2, and that is bigger than 1. So if our p-value, the exponent on that n, is bigger than 1, we can automatically say that this is a convergent series. Now we don't know the sum without extra work, but we know that it is convergent. In our next example, we have, again, a p-series. We can think of this as the sum from n equals 3 to infinity of 1 divided by n to the 0.9999. That negative exponent will push it to the denominator. This may help us visualize that it is indeed a p-series. Note that the initial series begins at 3. This is irrelevant since we're only determining convergence. We're not trying to find the actual sum. We just want to know, is it convergent or is it divergent? So again, recognize it is indeed a p-series. And so with that in mind, we look for p. P is the exponent on that n. 0.9999 is less than 1. So if your p-value is less than 1, we can say that this diverges.